A planet was hiding inside NASA's own telescope data for years, completely invisible to every standard detection method, until a scientist used a prediction Albert Einstein made over 100 years ago to pull it out of the noise and confirm it was there the entire time. NASA's Transiting Exoplanet Survey satellite, TESS, has been scanning the sky since its launch in April 2018, monitoring the brightness of hundreds of thousands of stars simultaneously and looking for the characteristic dip in starlight that occurs when a planet passes in front of its host star. This technique, called the transit method, has been the most productive planet-finding approach in the history of astronomy, responsible for confirming thousands of exoplanets in the Kepler and TESS era. But the transit method has a fundamental blind spot. It only works when a planet's orbital plane is aligned precisely enough with Earth's line of sight for the planet to physically cross the face of its star, as seen from our perspective. Planets orbiting at the wrong angle remain completely invisible to transit detection, regardless of how sensitive the telescope is or how long it watches. This geometric limitation means that for every planet TESS detects through transits, there are statistically many more planets in the same systems that transit detection simply cannot see. They are there, they are real, but standard methods produce no signal from them whatsoever. The discovery that broke this limitation used a phenomenon Einstein predicted in his general theory of relativity, published in 1915, gravitational lensing and its close cousin applied to stellar systems, called the relativistic beaming effect, combined with ellipsoidal variations and reflected light, collectively known when used for planet detection as the Beer algorithm, standing for beaming, ellipsoidal, and reflected light. Here is what Einstein's physics actually does in this context. When a massive planet orbits a star, three subtle effects imprint themselves on the star's observed brightness, even when the planet never transits. First, relativistic beaming. As the planet gravitationally tugs the star toward and away from Earth during its orbit, the star's light is very slightly boosted when it moves toward us, and dimmed when it moves away, due to the relativistic Doppler effect. Second, ellipsoidal variations. The planet's gravity raises tidal bulges on the star's surface that change the star's apparent brightness as the geometry shifts during the orbit. Third, reflected light. The planet reflects a tiny fraction of starlight back toward Earth as it orbits, creating a brightness variation synchronized with the orbital period. Each of these effects individually is extraordinarily small, measured in parts per million of the star's total brightness. But combined and analyzed together using sophisticated algorithms applied to TESS's precision photometry data, they create a detectable signal that reveals the planet's presence, mass, and orbital period without the planet ever needing to cross the star's disk. The specific discovery made using this technique identified a planet designated TOI 1431b, also cataloged as Mascara 5b, a hot Jupiter-class planet orbiting extremely close to its host star. But the broader significance of the Beer detection method being successfully applied to TESS data extends far beyond any single planet. It means that NASA's existing TESS dataset, years of continuous precision brightness measurements of hundreds of thousands of stars, contains hidden planets that transit detection missed entirely, waiting to be found by applying Einstein's relativistic physics as a detection tool. Researchers at institutions, including MIT, the Harvard-Smithsonian Center for Astrophysics, and international partner universities, have been systematically applying these relativistic detection methods to archival TESS data, effectively remining the same observations for a completely new population of planets invisible to standard analysis. Every star TESS has already watched for years potentially harbors undiscovered planets that this method can now reveal. The implications for understanding planetary system architecture are significant. One of the central questions in exoplanet science is how common multi-planet systems are, how planets are distributed across different orbital distances in a given system, and whether solar system architectures like ours, with small rocky inner planets and large gas giants in outer orbits, are typical or unusual. Finding the hidden planet populations that transit surveys miss fills in the gaps in that statistical picture with real observational data rather than theoretical inference. The technique also has a profound philosophical dimension that deserves recognition. Einstein developed general relativity to describe the fundamental nature of space, time, and gravity at the largest scales of the cosmos. He was not thinking about planet detection. He was not thinking about spacecraft or exoplanet surveys or photometric precision measurements. Yet a century after he wrote down his equations, those equations are being used as a literal tool to find worlds orbiting other stars, worlds that our most sophisticated telescopes cannot find any other way. The universe hid planets inside our own data. Einstein's century-old physics found them. The TESS mission continues operating, accumulating more stellar brightness data every day. As relativistic detection algorithms improve and are applied more systematically to the growing TESS archive, the number of planets pulled from the hidden population is expected to increase substantially. And when the Roman Space Telescope launches in 2027, with its 100 times wider field of view, the volume of stellar photometry available for relativistic planet detection will expand by orders of magnitude. There are planets hiding in the data right now that nobody has found yet. Einstein already gave us the key. We just have to keep turning it. So here is the question I want you to think about and answer in the comments. If Einstein's 100-year-old equations are still actively discovering new worlds in 2025, what other predictions from classical physics and general relativity do you think are sitting unused, that future scientists will eventually turn into entirely new tools for exploring the universe? Follow this page right now if the intersection of Einstein's physics and modern astronomy genuinely fascinates you, because the discoveries emerging from applying old theory to new data are some of the most surprising stories in science right now, and we cover them every single week.